Oh, why didn't you tell me? We should talk together. Didn't want to talk to me.
Well, not about it, you see that.
Oh, okay.
Sergey should be near the coffee machines. He will come in a minute.
Okay, good afternoon, PCS members and friends. Today we have a scientific seminar, which is a part of advanced study group activities. And our scientific host today is Professor Robert Schechter. Please introduce the speaker.
Okay, thank you very much. Good afternoon to everybody. It's a great pleasure for me to introduce Debashree Chowdhury. It's a member of our ASG group, and in her activity, which is actually in a different direction than what we have in our ASG group. She was graduated in the North Bengal University in 2009 and got her PhD in 2016 from Calcutta University. And since that, she was a number of postdoc positions in different places. Among others, I would notice the place. It was Beersheba University in Israel, when she met our respected members of our group, Ora Entin-Woolman and Amnon Aroni. And I think this was the beginning of their long-term collaboration. Different kind of physics they did together, mesoscopic transport, and charge, spin, heat in different kind of systems. And from Ora and Amnon, we got a strong recommendation to accept Debashree as a member of our group, which we did a couple of years ago, and we are very happy with this. She already made the presentation a year ago here on thermal transport in spin orbit active weak links. Today, she will tell a completely different direction of her interest. It's Weyl electrons in semimetals and subjected to microwave electromagnetic field and structure of electronic states under these conditions. So you're very welcome here.
Thank you, Robert. Thank you. Hello everyone. Today I'm going to talk about driven exceptional physics in topological systems. And this talk is based on these papers. So the outline of my talk is, first I like to give some explanation of the words that I have chosen for my title. So it was exceptional physics So I would talk about exceptional physics, which appears in non-hermitian systems. So I would briefly talk about what are those non-hermitian systems and what are recent experiments that are going on in this direction. And also I would, as we are interested in this non-hermitian scenario in topological systems, so I would talk about topology and what kind of different topological systems that we can obtain in various scenarios. And lastly, I would talk about our work, our results in driven non-hermitian topological systems. By driving, I mean different periodic driving and how to deal with this kind of periodic driving. So I would talk about the circularly polarized or and bicircularly polarized light. How do they affect this non-hermitian topological scenario that I would discuss. So let me start with the question that why do we need this non-hermiticity? Because in quantum mechanics, one of the major postulates is we have to have a Hermitian operator, and this Hermitian operator, why do we need this Hermitian operator? Because when we operate this operator on an eigenstate, we need to have some real observables or real quantities that could be measurable. So why do we need to introduce this non-hermiticity? So the first thing we need to understand that in quantum mechanics, we always deal with closed systems where energy is a conserved quantity. But there are systems where it is not. That is, we have open quantum systems. We have some dissipative systems where gain or loss of energy, that is the exchange of energy or particle with the environment, is always possible. So the whole scenario, that is the whole this whole work in the direction of non-hermiticity started with the seminal paper of Carl Bender in 1998. So what does he? So what is there in his paper? So he told us that the necessary condition that we need to have some observable, that is that should be a real quantity, that need not necessarily need a Hermitian operator. So if your system has some PT symmetry, that is parity time symmetry, and also your eigenfunctions are PT symmetric, one can have a real energy eigenvalue. So that was the beginning of the story. After this, many papers were there in photonic systems, especially because in photonic system, the radiation loss is a very common thing. So in those systems, many papers are there, theoretically as well as experimentally, which describes the exceptional physics and all this. So these are the papers. If you are interested in, you can go through. So the question is, then the question that appears in our mind is, what happens for an open quantum system? If you say, for example, consider a mesoscopic system which is added to a lead. So how do this non-hermiticity arise in those systems? So yeah.
Sorry, can I ask a question, please? So the previous slide, a very general one. Suppose I have one of these PT symmetric Bender, the two guys, Bender, Bettiol. Say I have one of these PT symmetric Hamiltonians, and I put them in a parameter range where the eigenvalue spectrum is real, because actually I can drive the non-hermitian Hamiltonian into a parameter range where it is the spectrum becomes complex, even though the system still is PT symmetric. But let's say the spectrum is real. Does it mean then, for some of these typical examples which are used in reviews, publications, experiments, does it mean that then also any observable, so to say, will be real valued, or can it happen that I define observables which are not real valued, like I don't know, momentum or whatever, or is that somehow granted? Or so because you started with saying that we want, where is it there? We want that
So in our
an
system,
observable should be real valued, otherwise how can we measure it? But
yeah.
how is that
So-
claim related to the properties of the spectrum of a non-emission?
Yeah, so in their problem, they have the real energy eigenvalues, but what we do, we actually allow the whole system to be complex energy, and there we calculate a certain things that I would discuss in our results section. So that can be measurable because you have even if you have the complex spectra, you have this is in the complex plane, so you can have some real energy spectra and imaginary energy spectra. So using those, you can calculate the Berry curvature, which is a real quantity. And using Berry curvature, you can identify your topological states that I would discuss.
Thank you.
Yeah. So I was about to tell that how do these non-hermitian terms appear in say, for example, in an open quantum system. So it is very beautifully discussed in this paper. So what they did, they consider a material junction, uh, which is a junction of some topological material, specifically a topological insulator, and it is connected to some ferromagnetic lead. So what they found is basically when they are very close to the surface, they can write an effective Hamiltonian for which includes the Hamiltonian of the topological material plus the self-energy term that comes from the ferromagnetic lead. So this uh, self-energy term actually contains two parts. One is real and another is complex or non-Hermitian. So that actually contributes to the non-hermiticity in the system. So apart from this, we can also consider cases where the electron or electron phonon interactions are there. So in this paper, Liang Fu has showed with his collaborators that in this system also we can consider a self-energy term and we can write an effective theory where this self-energy term contributes to the non-Hermitian part in the system. So these are actually the mechanism with which you can have a non-hermiticity in the Hamiltonian. So let me discuss the physics behind this non-Hermitian systems with a very simple matrix. This is basically Hamiltonian, which is a 2x2 matrix, where this alpha is a complex quantity. So say, for example, for this Hamiltonian, we calculate the eigenvalues. So these eigenvalues are plus minus square root of alpha. And you can also calculate the eigenvectors. Now you need to understand that your H and H dagger are different. So you have two sets of eigenvectors. So first one is the right eigenvector and the second one is the left one. So you have these two eigenvectors and they constitute a bi-orthogonal quantum mechanics. Bi-orthogonal quantum mechanics means that your psi r bracket is always 0 and psi l bracket is always 0. So this psi l and r bracket gives you this orthogonality condition. So that's why it is called the bi-orthogonal quantum mechanics. Now we can calculate this psi r plus minus and psi l plus minus with this kind of a structure. Now the question is, what happens when we take alpha equal to 0? So if your alpha is 0, then you can immediately identify this matrix as the Jordan block. because it cannot be further diagonalized. And at alpha equal to 0, your energy eigenvalues are that is, we have some E plus is equal to E minus, and your psi r plus becomes psi r minus, and psi l plus becomes psi l minus. So one can identify that at alpha equal to 0, you have not only you have a merging of your eigenvalues, but also some of the eigenstates are merging. So this alpha equal to 0 is called the exceptional point, where not only your eigenvalue, but also your eigenstates are merging. So what happens at those values? At those values, as I have mentioned, that your linearly independent eigenvectors are less in number than the algebraic multiplicity, that is the degree of degeneracy of the characteristic polynomial. So what happens at those exceptional points? So let me write this alpha as it is a complex quantity as some mod of alpha and some argument of alpha. So if we do so, then your E, which was square root of alpha, then becomes alpha to the power half and the argument of alpha by 2. Now, say for example, you consider a closed loop around this alpha equal to 0 point. So if you do so, and you take the value of argument of alpha from 0 to 2 pi, then what happens? You have, apart from this factor, you have some e to the power I pi, and this gives you minus. So your E plus becomes E minus, and your psi r plus becomes psi r minus. So what does it mean? So if you start from this point in the band structure, after 2 pi rotation, you go to this point, which is S1. So you do not return back to your original point after 2 pi rotation. So to return back to S2, you need another 2 pi rotation, and you just come back to S2. So this is a very common thing in multi-valued function. As we know from our complex analysis course, that this is common to a multi-valued function, and this point alpha equal to 0 is the branch point, and we have some branch cut also in this system. So it is basically a two-valued function, not multi-valued. So this structure, this band structure, that is, we go to S1 from S2 after 2 pi rotation and return back after 4 pi rotation, is basically a double Riemann sheet topology. So this is very basic things. Now I would like to mention what happens for a two-band model. So what happens for a two-band model for a Hermitian system? So a Hermitian system is basically a dk dot sigma. Ignore this D0 term. This actually gives you a shift in your spectra. So if you calculate the energy eigenvalues, this looks like this. Now, to have the degeneracy points, you must have E plus is equal to E minus, and this needs to satisfy three equations, that is D1 square equal to 0, D2 square equal to 0, and D3 square equal to 0. So we need three equations to be satisfied in a Hermitian systems. So what happens to a non-Hermitian systems? So we start with a same two-band model, but here your dk contains some imaginary part as well. So your E plus minus becomes this. So you have a real part and also an imaginary part. So to satisfy E plus is equal to E minus, you need to satisfy this equal to 0 and dr dot di equal to 0. So we have only two equations here. So this is easy to handle, first of all. And second thing is, one can question that this is also valid for dr is equal to di equal to 0. So that gives you a trivial scenario where your eigenvalues are definitely, we have E plus is equal to E minus, but we don't have the condition for the eigenstate. So which is important for the exceptional points. So for only this condition, we get the exceptional point. So we can choose a curve on which this condition is satisfied, a closed curve. This is represented by this black one. And we can also have a closed curve for this, which is denoted by this dotted line. And when both of them are satisfied, this gives you the exceptional points. And the arc in between is called the Fermi arc. And if you want to know more about these, so you can go through this beautiful review of 2021. So these are very basic things, and this is the experiment where these Fermi arcs are obtained experimentally. So this is a paper from 2018. This is a science paper, and they have taken a photonic crystal and they illuminate it with a laser, a specific laser, and they analyze the scattered waves. And when they analyze the scattered waves, they found some isofrequency contours. So these are for simulations and these are for experiments. And you can see this isofrequency contours. And for a specific frequency of the incoming wave, the laser, the that is illuminated on the photonic crystal, we have these open-ended arcs. And these arcs are the Fermi arcs they are obtaining, and the exceptional points are somewhere there. So it actually contains two exceptional points, and in between we have a arc-like structure. So that is obtained experimentally as well. Now I would switch to the next topic, that is topological systems, because we are interested in topological non-hermitian systems. So what is topology? That is a mathematical scenario, and that is in mathematics, topology is connected to some geometry. So suppose we have some plate or a ball. So these are topologically equivalent in the sense that you can smoothly deform the plate into that ball. So by smooth deformation, I mean I do not use any cut to make a hole in between. So the number of hole is very important in this case. So so mathematically, these plate, the ball, or the cupcake is different from a coffee cup or a donut because they are topologically different in a sense that one cannot simply jump from this plate to a donut. So you need to have some destructive action of creating a hole. But a coffee cup can be smoothly deformed to a donut. So these are in the same different topological class, and this topological distinction is made with the help of this genus, that is G. For a ball, G is 0, and a donut, G is 1. So what is the analogy in physics? So in physics, we consider the smooth deformation. But in physics, the smooth deformation means you have a system and you have a Hamiltonian. You smoothly vary a parameter in the Hamiltonian in such a way that your band gap is not affected. So if you can smoothly deform an insulator to other insulator without affecting a gap, then we can say that these two insulators are in the same topological class. So, but if you need to have from an insulator to some other material, so you need to go through some kind of a destructive action, which is denoted by a gap closing. So that I am not going to discuss. But anyway, so in physics, the determining quantity that quantifies that whether the system is a normal insulator or has some topology is determined by the Chern number. So the notion of topology and the Chern number was first introduced during the very famous effect and during the establishment of this quantum Hall effect, and von Klitzing in 1990 experimentally have shown that in certain systems, say for example, a two-dimensional electron gas, when it is placed in a very high magnetic field, one can have a quantized Hall. The conductivity, Hall conductivity is quantized. So this quantization factor is called the Chern number, and this is very interesting to quantify systems, whether it is topological or non-topological. But the thing here, the important thing I'd like to mention is that here the time reversal symmetry is broken. So people started looking at materials where the time reversal symmetry should be intact, but still we have some interesting effect associated to topology. So it was the birth of topological insulator, where which is shown in the HGT CTT quantum Weyl. So this Mercury has a very high spin orbit coupling. So because of that, it shows some band inversion in the system, but CDT shows the same band structure. So for a particular depth of the Weyl, one can have a topological insulator in this system. So in topological insulators, we have the bulk is insulating, but we have conducting edge states. So I'm not going into that detail, but the system we are interested in is multi-Weyl semimetals. So after the birth of topological insulator, there are many more other topological materials that are discussed in the literature, and one of them is the Weyl-semimetal, where this is gapless in the bulk, and we have the conduction and valence band touch each other at the Weyl point, and these Weyl points are the source or sink of monopole charge of +1 or -1. So this is for the normal Weyl semimetal, but we are talking about multi-Weyl semimetals. So this is the situation that appears in many materials. Say, for example, this material, now which supports this double Weyl structure. So where your single Weyl nodes, so two single Weyl nodes having charge +1 is come together and make a +2 or double Weyl semimetal. So this happens due to high spin orbit coupling of the system. So in that sense, we can have a triple Weyl semimetal as well. So these semimetals actually have some rotational symmetry, which is a point group rotational symmetry of C4 or 6. So I would talk more about it, but to give you the introduction of this kind of a system, I added these parts. So what happens for the exceptional points in this kind of a system? Say, for example, I consider a 2D Weyl cone and have given different kind of perturbations. Say, for example, if we give the Hermitian perturbation, epsilon sigma z, it is gapped out. So this is the scenario with Hermitian perturbation. Now, if we add some perturbation which is non-Hermitian, but along sigma x, that is off diagonal part, so we have the exceptional points, and also one can witness the appearance of exceptional ring, which contains the exceptional points when your when your perturbation is along the sigma z. So these are the scenario one can obtain, but I will talk about our results in the last portion.
Can I ask a question, please?
Yeah.
I imagine I have a piece of that material with mercury and so on, and Weyl semimetal. What physically should I do to have this I, BZ, sigma Z perturbation or something different?
Yeah, yeah.
Something similar.
Yeah, yeah.
What
That-
physically should I apply to my material?
Yeah. So basically, this kind of systems are discussed in photonic, different photonic systems where we have two sublattices and you apply, in one lattice, you apply some gain and in another one, you apply some loss. So if you do so, then you can have uh, this sigma X perturbation. Now, for a different combination, you can have a diagonal contribution. So it is experimentally also people had done. So this is the thing actually. So, and also, as I have mentioned previously, that you have some self-energy term. So this self-energy term can also give you, theoretically, if you understand, then this can also give you some kind of a sigma X or sigma Z term, depending on what kind of lead you are adding and all this. Yeah.
But I mean, if you have self-energy from Hermitian Hamiltonian initially, you cannot get wrong sign of the imaginary part because in that case, your system will blow up. You will always have some damping due to self-energy. In Hermitian, if you start from some Hermitian Hamiltonian with field theory and so on, or you have an instability from the very beginning. That's, I think.
Open system.
No, here we are talking about the effective Hamiltonian, and this self-energy part has a real part and an imaginary part. The principal value and the imaginary part, that is I gamma delta kind of a part. So that actually contributes to your non-hermiticity in the system.
Okay.
Yeah.
Is it important to have microwave fields for have this non-hermitian behavior or not?
The boundary cover the boundary.
And so
So
you think that it's self-energy can have the gain?
Exceptional points.
Boundary, you have the deduct code.
Okay.
The boundary top to the bottom
Yeah.
also.
Yeah.
So you can get a frequency on the boundary.
So we can continue.
Of course, yes. We are just
Let's continue.
Introduce exceptional points and how that I assume that it's not so non-hermitian systems.
what?
So
You can continue.
okay. So experimentally also, in some waveguides, in helical waveguides, this kind of a appearance of exceptional physics is discussed in this paper in Nature Photonics 2019, where you can say that where the non-hermiticity is introduced by periodically skipping the writing of a specific length of those waveguides. And you can see that for a particular kind of a perturbation, we have exceptional contours and we have exceptional points for some other kind of perturbation. So here also they have discussed this. Why do we need to consider sometimes the sigma X kind of a perturbation, and for other case it is sigma Z. So by properly adjusting this skipping of the writing, in two sublattices, as I was mentioning, that one sublattice contains some gain and another sublattice contains some loss, and this gives you the desired configuration. So anyway, I am in the last part of my talk. So this shows the role of driving on this non-Hermitian topological system. So we all know about the Bloch theorem, and it actually shows that your Hamiltonian has a space periodicity And similar to that, if your system has some time periodicity, then you can write your eigenfunction as some exponential part with some ut, similar to the block case. And your ut is basically periodic, and this part contains the quasi-energies similar to your quasi-momentum in this case. And as we all know that if we replace this k by k plus g, it remains the same. Similar to that, if you replace your epsilon alpha with nh cross omega, where n is the number of photons, it remains the same. So this is the basic thing in Floquet theory, which we would apply in our systems. So what we do is basically, for the first case, I would talk about the circularly polarized light, and we consider the electric field as this. So if we do so, now to do this, to analyze the system analytically, we consider the high frequency approximation, where it is considered that your omega, which is the frequency of the light, is far large than any energy scale in the system. So the energy scale, by energy scale, I mean the bandwidth. So it is larger than the bandwidth of the system. And if we do so, then one can write the high frequency approximation, where we have some effective Hamiltonian, and this effective Hamiltonian carries no time dependence. This is independent of time, because in this calculation, we consider the time dependent part and take its average over a single period. So because of that, finally, we don't have any time dependence in the effective Hamiltonian. And we calculate different orders up of 1 by omega. So I kept only up to order of 1 by omega, but one can also consider orders like 1 by omega square, 1 by omega cube, and all this. But I stick to 1 by omega because omega is very high. So if we do so, let me discuss the results of our paper. So this was the first paper in this direction, where we considered the light-driven transformations in non-hermitian multi-Weyl semimetals. So this is the Hamiltonian of a multi-Weyl semimetal. And as you can see that this Q plus minus is this, and sigma plus minus is this. And this zeta is the gain parameter, which I have discussed that it is proportional to sigma z. And the energy eigenvalues we have are like the square root, have the square root singularity. So, but we need to add some driving in this case with the circularly polarized light. And if we do so, then what happens? We add some delta part here. We obtain this, where delta has the information of the amplitude and frequency of light. Now the
Yes.
question is, yeah.
Previous slide. Could you give a previous slide?
Yes.
The psi, is it has to do with the microwave field, or you say?
So here omega is very high, so it's actually for a microwave field, you are treating this electric field as classically. But here it is we are talking about we are dealing it as quantum mechanically, and we have the Floquet theorem for that. And yeah.
In the absence of electromagnetic field, psi will be zero or not?
Which side?
If microwave field is absent.
Oh, yeah. This delta is zero.
Zero?
Yes, delta is zero. Yes.
Okay, so
yeah.
you see
Delta is zero. Yes.
Imaginary part by put in microwave.
No, I
field.
don't understand. She said that delta will be zero without the field, but what about zeta? That's
Zeta will be zero. She said.
also.
This is non-hermitian part. This is not zero.
Not emission, but
Sorry, what?
microwave field.
Was there some expression for zeta before? Maybe I'm.
Yeah. That was before also.
Zeta
The
gain.
gain
It's
parameter.
just a parameter.
It's a parameter, yeah. Yeah.
Gain.
So you create non-hermicity by microwave somehow.
And with the time dependent field, we are adding some extra handle, but it was previously it already have a non-hermitian parameter. It already has it before application of this driving.
So I was wrong.
Yeah.
Thank you. You continue.
Yeah. So one thing that I forgot to mention here, that you can see that your sigma x and sigma y has some rotational symmetry in this case. If you replace the sigma y by sigma x, you get the same result. But unfortunately, this is not the case when we have the driving. So because of that, we actually lost the rotational symmetry of this system, because if you replace this qx by qi, you get something else. So these are the band structure for our system. So first of all, when you have no driving, you have the exceptional physics, exceptional contour. So this is for the double Weyl case, and we have here the charge of the exceptional contour is +2 or -2. Now, if you apply the driving in this case, you have two exceptional surfaces which has charge equally distributed, that is +1 and +1. And the third one is for triple Weyl, that I am not discussing it here right now, but I will discuss it later. So the point is that is clear from this band structure and also from this contour structure, that previously it was one single contour, exceptional contour, due to the presence of the non-hermitian part. And when you start applying the driving, the single contour starts breaking, and we have two contours from this. So this is something interesting, because you are producing some new exceptional contours, which is interesting with the help of the driving. And here we have shown the different exceptional points that are appearing in the system. And with these points, one can also calculate the vorticity that I would discuss next. So basically, we have different type of topological invariants in this non-hermitian systems. These are the Chern number, vorticity, and winding number. So the Chern number, we all know that it is the integral of the Berry curvature. But now the question is, what Berry curvature we are talking about? Because here we have left-right eigenvectors. So you need to calculate your Berry gauge field with the help of this left and right eigenvectors. And if you do so, then you calculate your Berry curvature with the help of the this formula, and this actually gives you some real results that is obtained in various papers. And also you calculate the Chern number with the help of this formula. And what is the value of this Berry curvature for our case, that I would discuss. But the vorticity, which is another important parameter or topological invariant in this non-hermitian scenario, is obtained with the help of the eigenvalues. This is the criteria. And you can see that you need to have integration over a closed surface. So here, the closed surface means the surface should enclose your exceptional point. Otherwise, your vorticity becomes 0. if your exceptional point is enclosed in the surface, the vorticity becomes fractional, that is half. And this fractional vorticity is a major identification for these non-Hermitian systems. So we are left with the winding number. The winding number one can calculate for these systems, and it is more or less similar to the vorticity, and it shows again the fractional values when this actually encloses the winding. It encloses some exceptional point. So the number is plus minus half or half, or if you have two EPs which is enclosed in the loop, then it can take values like 1 or -1 or 0, depending on the winding direction. So if we take an EP, and if its winding direction is different from the other one, then we can have a 0 also in this case. So this is the Berry curvature that I have previously talked about. Now in our system, for a double Weyl case, we have shown that when we don't have any driving, then this red curve shows that the charges are piling up in one location. That is also confirmed with the contour diagram also. So charges are piling up here. Now, when we apply the light, then what happens for a particular frequency and amplitude? We get that we have two positions where the charges are piling up, and these two positions, this shows that your charge is divided, that is the charge division is taking place here. So this is something interesting that was shown in this paper of ours. And now I would talk about the last one, that is this paper where we discuss the bicircularly polarized light. And to discuss that, let me discuss first what is bicircular light. So a bicircular light is basically two superimposed circularly polarized light. So you can consider like this. So you have a light like this and another like this. This is the gauge potential. And if you draw this gauge, okay, so I did not mention what is N1 and N2. These are the two frequencies of the light. This should be different, and you have a difference in the phase also. So if you have that, then we can have some rose-like patterns depending on the ratio of the two frequencies. So if we apply this kind of a bicircularly polarized light, which has a rotational symmetry of N1 plus N2 by this, which is the greatest common divider. So if we have this kind of a rotational symmetry, then what happens if we shine this light on a particular system which already have a rotational symmetry? Say, for example, the multi-Weyl case, which already has a rotational symmetry. And if we apply this kind of a BCL on this, so this actually modify the rotational symmetry of the original system. So for this, we have written the effective Hamiltonian for the high frequency approximation and have calculated the energy eigenvalues. These are huge expressions, so I have not mentioned it here. So what we are getting, so previously with the circularly polarized light, we get for a triple Weyl case, we get 3 exceptional contours. And it is found on the zero energy for real energy 0 and imaginary energy 0. This is the criteria of having this exceptional contours. But here, what we are getting is we are getting some interesting surfaces, some double nodal ring structure or some self-linked structure that actually gets dissolved, and we have some open-ended arc-like structure. So we have, so the point is whether these figures are exceptional, that is whether we have the exceptional physics in this. So the answer is, answer can be obtained from this plot, that we are not getting always the exceptional physics. That is, we are getting it here with, so these figures are for real energy with this K, which K is root over kx square plus ky square. And if you tune the parameters of the system, one can show that we not necessarily always get this exceptional physics all over, but definitely in this kind of a system, we have some swapping of imaginary bands, not in the real band. And because of that, you can see it from here. These are the imaginary bands, and we have the swapping between it, and this causes the different structures in this system. So what happens in this system is basically some renormalization of the rotational symmetry, because your light has a rotational symmetry and also your system has a rotational symmetry, and this causes some renormalization of the rotational symmetry. So these are the plots for Berry curvature at the space diagram. So I'm not discussing it right now because I think I'm running late. So these are the possible experiments in this direction. So as I have already mentioned that experimentally one can see these exceptional contours in helical waveguides and all this. But apart from that, there are huge craze on these topoelectrical circuits where by some series of conductance resistance, you can design your this non-hermitian topological systems, and these are discussed very well in these papers. If you are interested, you can go through these papers. And so I come to the conclusion. So this is the summary where I have talked about this multi-Weyl semimetals and different kind of driving. I talked about Berry curvature and charge division with the circularly polarized light, and with the bicircularly polarized light, I get some kind of different Fermi surfaces that need not necessarily always be exceptional. So thank you for your attention.
Thank you very much. So now it's time for questions, please, if somebody. Please.
Okay, thank you. So Fouquet theory is well known to work well with single frequency driving. Now, if you have two periodic driving, especially if these frequencies are not commensurate, would you expect that limit of that, which you can check experimentally quite easily here, would lead to complete breakdown of your topological structure to some sort of transition into totally new phase of this topological matter, or it wouldn't come?
So it's a superposition of the two circularly polarized light, and so these are designed in such a way that you have the information tuning parameter like N2 by N1. And with this, there are plenty of experimental work also going on in this direction. So it is perfectly all right if we apply this kind of a BCL light to topological systems. It doesn't ruin your topology. That was, I have not mentioned so one of them is this nature communication. So there are other plenty of papers that people are working very hard in this direction. So this is completely fine to work with this BCL light in this case.
What if N2 over N1 is equal to square root of 2, for example?
So I have not talked about all this. So basically this AL and AR, these are, you can take different or same. So that I need to check why this is root 2, that I forgot. But these are basically vectors which actually contains the information of your incident direction. So in which direction it is incident. So that is incorporated in this. So suppose I think that because of this epsilon L and epsilon R, this two factor is coming. So I need to check it again. Yeah.
More questions? I have a question. I mean, how experiments should look like? I mean, for example, to check it, you should organize somehow scattering of the microwave on your material and analyze scattering or analyze the microwave field in vicinity of metal or absorption. How
For this PCL, or are we talking about? So experimentally, so I have discussed this experiment. Yeah, this one. So suppose you have a sample and you are illuminating it with some laser light, what they did actually, and you are looking at the scattered light. So the yeah, and you are looking at the scattered light, and they have this isofrequency contours in the R-pace experiment. So that could be one possibility, but I need to think about it experimentally, how to design such a case. But anyway, so what was your question? Sorry.
No, I just understand the setup for that. Could
Yeah.
we say like this, that observation of contribution of this exceptional physics in this scattering picture would be indirect demonstrations that systems are described by non-hermitian Hamiltonian?
Yes, yes, yes.
Is it correct? I mean, is there any more direct manifestations that system can be described or should be described by non-hermitian Hamiltonian?
Yes, yes. Yeah. So so the non-hermitian Hamiltonian, you can also consider this kind of a setup. Here they have some helical waveguides, and these helical waveguides, basically bipartite array of helical waveguides, and they introduce the non-hermitianity by periodically skipping some portion of it. I mean, the writing, I don't remember what is writing here, but they have skipped a certain portion periodically, so that they have the non-hermiticity is introduced in the system. And because of that, they are getting this contour and then exceptional points in this case. Yeah.
So is it like this, that to have this non-hermitian Hamiltonian, you have specially tailored system? You should do something with the system. You should apply to the system something.
Yeah, so I have shown the topological scenario. So how new topological phases can be obtained. But there are also many more other aspects of non-hermitian systems. Say, for example, the skin effect, which is a very important scenario nowadays, where the eigen states are piled up in a particular age. So that is also very interesting, and there are many more directions nowadays. So if you are interested, yeah.
More question? If there is no question, thank you very much for very interesting.
Thank you. Thanks a lot.